Okay, great. So let's start this talk. So first, let's start at the beginning. Let's call this track of zero, like introduction. So what is our main object? What is our main character of this talk? I'm going to talk about the group of automorphisms of X. What do I mean by that? Of course, X is a topological space. And we consider the group of maps up to homotopy from X to X, which preserves base point. So the first remark here, that in this talk, I'm going to assume that X is simply connected. Therefore, there is no difference between considering base point automorphisms and non-base point automorphisms. Just keep that in mind. And for proper motivation, let's consider a simple example. Like how automorphism of X can look like. Let's consider the simplest from homotopy theory point of view space. X equals to Eilenberg-MacLaurin space of Pn, where P is some finitely generated abelian. And well, since X is simply connected, N is necessary greater than 1. So what one can say about it automorphisms? I propose that automorphisms of X, well, let's say X is controlled by the group P. So it's not a surprise that automorphisms of X are precisely the automorphisms of P as a group. Okay, let me not prove it. I will assume that it's kind of non-fact. It's not this exercise in abstraction theory. If you want to know why, I can prove it, but okay. So now consider rational localization of X. How does it look like? It's look very simple. This is some map like this. P should be tensored by Q and the same N. This is localization of our KPN, and the map here is just R induced by the natural map P goes to P tensor Q. So what do we know about automorphisms of rationalization? It's not very hard to describe as well. It's automorphisms of P tensor Q. Yeah. So note that this is precisely just some invertible matrices precisely of some vector space. Yes, which vector space are is P tensor Q, which is finite dimensional since P is finitely generated. Now, consider shells. Now, denote by the free of P. It is
well. There's a small remark here. The automorphisms of P tensor Q as a group are the same as the automorphisms of, as a Q vector space.
Yeah, yeah, it's true. I didn't say this, but thank you for this remark. It's really important. Okay, so let's consider free part of the P. It's phi of factor of the all torsion elements of our finitely generated group. And since our group is finitely generated, the following map first is defined since I will write it. It is defined since an image of any torsion element lies in the torsion group. So you can take factors and everything's gonna act on that. And moreover, kernel of this map is finite. Wait, finite. No question here? Okay. So, but what is automorphisms? So we have map automorphisms of free P to the automorphisms of P tensor Q, which is just, well, no, that free of P is just some Z to the power of N. And so what do we see here? We see here that automorphisms up to some finite ambiguity, which is somewhere in the torsion, is included in the some group of matrices, say like this, as some integer points, let's say something like that. And so how can I say it? The main objective of this talk is to prove that this is the case for a lot of x's. Let's say it's a theorem, because I won't formulate it correctly right now, but I will later. That if x is simply connected, so I just and finite dimensional, then it is, well, let's say it's like this. This is very informal, but formulated correctly later. It is like integer points automorphisms of x is group of automorphisms is integer points of some.
Well, the word it is tricky. The word it is tricky. So let's write out x instead of it.
Since someone can write it, then let's say it's like, sorry, okay, or some linear group. Yes, we have a group of matrices up to some finite ambiguity. I don't remember how to write this word, but let's say it like this. Неопределенность.
Has anyone seen the film Monty Python and the Holy Grail? Смотрел ли кто-нибудь фильм насчет Монти Пайтона про Святой Грааль? Okay, well then let's continue.
Okay, давай. So this is my main objective, to try to prove for you this theorem. So first, this condition is not vacuous. For example, this implies, for example, corollary that automorphisms of x, let's denote it as gamma. That's gamma is, for example, finitely presented. Say, and say that specifying space, just for example, is of so-called finite type. This means that classifying space have the homotopy type where you have finite number of cells in each dimension. So this theorem really just gives some information about automorphisms. It's not just some vacuous condition. which don't tell anything. Okay, so I think we're done with introduction, and I think I can move on. Is there any question on this paragraph or not? Okay, so is there no question? Let's continue. Now, we would like to formalize what up to finite ambiguity means. And so for that, we need some algebraic intercourse, algebraic introduction. Let's say it's a very brief intro in arithmetic groups. So we would like to somehow describe so-called integer points. Okay, so first definition, but you probably know it, but just to set a convention, notation, we will call group J is a chi, where chi is a field, linear, algebraic, if J is an algebraic set, a solution of some polynomials in group of GL of V, where V is some finite dimensional vector space over K. Okay. So now fix some lattice. In order to define what arithmetic group is, fix some lattice L. It's lattice. Maximum discrete group of maximum rank. And
what does discrete mean if we are over an arbitrary field?
No, it's fair. It's fair. I think that yes, we should fix fair point. So let's fix one for all, like for this talk. We wouldn't care about any other fields. We will take equals to Q. So then lattice now makes some sense. Okay. Okay. And consider denote, let's call definition again. That J with subscript L, it's just some element of J, such that J of L equals to L. It preserves it. Okay, so let's consider some example which show why it's somehow an idea of integer points. Let's say, well, if you fix some basis, concrete basis of V, and we can consider the following lattice. It's gonna be just lattice which is spanned by these vectors. Then identifying GLV with set of matrices via this basis of YIT, we get that G of L, G of L is precisely the like matrices with integer coefficients, and with condition the determinant is equals plus minus 1. Okay. So this is some example. Now we see that actually the construction, actually depends on the choice of lattice. So it's not really well defined right now. So we need to somehow find out how our group changes by rechanging the lattice. Well, the following theorem says that it changes not so much, a little bit. Okay, let's call it. Well, I don't know. I don't think let's call it proposition. that say L and L prime is some lattices. Let's say in one vector space for now. And then in the intersection of GL and GL prime is subgroup of finite index in GL and GL prime. Okay, so let me look at time and think whether should I prove it or not. Okay, no, I want to prove this something in this paragraph. So let's briefly say how to prove something like that. First, note that, but without loss of any generality, we may assume that we may fix basis like in the example above, and we may assume the L as there. So L is just, I will denote it like this. I mean, it's not some beautiful notation, but probably it's understandable. Okay, now consider some map.
So why are we allowed to assume that L is free Wheelan?
Lattice, which would be free right now.
Once again, the lattice L is a lattice in V or in G?
In V.
Okay. Потому что, значит, в обоих случаях имеет смысл, значит, имеет смысл решетки и, значит, немного разные решетки.
Ага. Вот тут здесь just in vector space. And everywhere above, I meant lattices as in vector space, not in line subgroup G of shell vector. Okay, now consider some. Great. Now consider map from V to V as a Q vector space, which sends lattice L to L prime. Yeah. So such map existed. It's some matrix with rational coefficients. Yes. So since well, what do we know this? Just I think that I yes. Sorry. Right. This. So know that using this map. We can define. We can. How can I say it? Like, okay, I'm better to explain, but say we have some inclusion by definition. Okay, let's say this inclusion iota into GL of V. And so we can actually like post-compose it with this 0. Like just multiply by the matrix, which is represented by rho. And take and have and another, sorry, some problems here. Another inclusion, which is called, let's call it, I don't know, iota with subscript rho. So now we just need to understand how does the group of this GL prime is gonna be just some group of J. Since the image of our lattice L prime is just standard lattice, so it just the condition of preserving is gonna be like this. Okay. since the image is standard lattice. So when does matrix save an integer lattice, preserve it? Well, let's say, okay, let me write another way. Since row of identical matrix is identical matrix, the matrix, so row of J is going to be a matrix with entries as polynomials, linear polynomials in entries in the J. And it's going to look like this. It's going to be here 1 plus some polynomial without constant term. Here we just have on the second position polynomial without constant term. Oh, I didn't complete it. And so on. And the second, we just can hear this polynomial.
You've written with instead of without.
No, without should be. I just didn't put enough space to write it. But
There's a way to abbreviate without by writing W/O.
Fair point. Thank you. 1 plus without const. Okay. And so on. So now note that how does this polynomial looks like? This polynomial are some polynomials with rational coefficients. Yes. So since there's just some finite matrix and we have finite number of polynomials here and finite number of coefficients, so there exists M such that if J is if elements of J, let me say if J is equals to identical matrix mod some integer M, then row of J is M matrix with integer coefficients. Because in that case, we just need to take M like take multiplication of all знаменатели. I don't remember how to say it. No, I hope this is clear. I mean,
Well, let's ask the audience. Ashok, does this argument make any sense?
No, I didn't finish it yet. Like, but
well, at least what has happened so far.
Yes, yes, makes sense.
Great. So now we need just to note that a group of matrices, subgroup of J, which satisfies this condition, first it's subgroup because it's kernel of some map, like say, induced by it's kernel of some map, and it is obviously of finite index, like because factored by this group is just gonna be matrices with coefficients in Z factored by MZ or something like that, and it's just finite number of matrices there. And so this is some subgroup of finite index, and this subgroups is obviously preserve our integer lattice, and the left just need to notice that GL prime intersect with G of L contains this, let's call this group, I don't know, gamma with subscript M, like this. So this intersection really contains gamma. And well, since gamma is so finite index, then the intersection is as well. So this is the end of the argument, and we're done. Okay. So now, from this theorem and from the example above, we can make a definition. It's kind of motivates it. Let's call group J and R are commensurable.
Commensurable.
А там написано, ну, я видел commensurable. Okay. If they lie in the same equivalence class generated by the following morphisms. So, and let me write which morphisms first. First, we need to morphism like, let's say, G1 is in G2, a subgroup of finite index. So our definition of the JL makes sense right now. I mean, at least the equivalence class doesn't depend on it right now. And the second one, which is motivated from our example, maps like this. It's going to be a surjection with a finite kernel. So this is what I meant by finite ambiguity in the previous paragraph, precisely. Now, the definition, finally, what is an arithmetic group? Definition. Arithmetic group, let's call it H, is by definition group commensurable to a group of type GL. And now, since we started it, let's now finally formulate our theorem in a little bit more precise way. Or maybe I should wait, let me think. Yes, so no, let me just formulate some properties which is going to be useful in the proof of theorem. No, let me formulate theorem first. I'm just sorry. Theorem. Now the same. If X is simply connected, topological space, and X is finite dimensional complex. Then the group of automorphisms of X is arithmetic. Oh, so that is, before I continue, is there any question on formulation of this theorem? Okay, so if not, let's continue. So now I think I will just formulate some properties because I don't have a lot of time. Let's just say, I'll formulate just one property. I don't think I have any. Let's say by definition, sorry. Let's say that a homomorphism of group realize J as an arithmetic subgroup if 2-point holds. First, the kernel of homomorphism R is finite. And second point is that image of R intersect with, what should I say? Yeah. So I forgot another point. H is a Q-linear algebraic, and image of R intersect with, oh, this is bad notation. Let's say it chi of L. This is subgroups with which we got from lattices. Yes, is a subgroup of finite index in image of R and L. So in particular, J is an arithmetic subgroup. Like, okay. Now,
sorry. So here H is arithmetic group.
yeah.
Okay. Thank you.
Thank you for the questions. Now, let's say it's property, which I think I won't be able to prove right now, but which is like gonna be very important in the future in our induction step in our proof. Let's say if we have an exact sequence of groups, let's say it's like J1, J2, J3, and 1. There's some exact sequence, not necessarily abelian groups, but some, and we have this row H1, H2, H3. Well, now H's are not just a group, but a Q-linear algebraic groups. And assume we have maps of these exact sequences. Let's call it R1, R2, R3. Well, you can guess, since I already kind of spoiled that it's can use in some kind of induction. If R1 and R3 realize GIS an arithmetic subgroup of HI, then so is R2. So this is the formulation. Let me show it again. It's like, it's going to be very useful in the future, so I propose to you to try to remember it. Now, I think I won't be able to prove it, but it's too long. Yes, it's too long. I think I don't have enough time. So let us move on to the next section. So we kind of discussed what an arithmetic group is in a very brief way, but it is what it is. Now we're just, in an example we had that the automorphism group of our rationalization is somehow a Q-linear algebraic as well. Well, it was just Charlotte Webb, but it's a particular case of Q-linear algebraic. But like, is it true in the arbitrary case? Yes, like, and this is what we're gonna find out in the next paragraph. Let's call it paragraph, it's 2. Let's call it automorphisms of animal models. Now, here in this paragraph, our main object is just some rational topological space. Let's call it X with subscript 0. And we would like to understand that automorphisms of X0 is Q-linear algebraic. Or what do you need to impose on X in order for that to be true? Now, we know from rational homotopy theory, like the most important theorem, that automorphisms of the rational space is precisely automorphisms of its minimal model. Yeah, the take X, so its minimal model exists. I think so. And factor out by some maps of differential graded algebras homotopic to identity. Now, we would like to understand whether the group here is algebraic or not. First, let's consider the automorphisms of M. If automorphisms, oh no, not automorphisms, I'm sorry. If M is, let's call it, I don't know what's the term for this precisely, but let's call it bounded. The differential traded algebra. This means that the corresponding differential complex is bounded. Then automorphisms of M is algebraic. Well, it's not hard to understand because we just need one condition of commuting with differentials, with which are just some algebraic equations. So automorphisms of M is very easy to understand that it's really some algebraic set in the generality way. I probably explained it poorly, so if anyone have questions, then I would be okay. So since everyone understands, it's good. Now there are two, like some kind of dichotomy where this happens, where M is bounded. Let's say this happens if M is bounded in the following cases. If X is finite dimensional, not that finite dimensional, it's kind of the complex, but it's better to say that it has finite number of cells.
By the way, what exactly do we mean by saying M is bounded?
Yes, I've said. I mean that's corresponding complex is bounded. Like,
so, do you mean that the complex that M as a complex of vector spaces is bounded above? Значит, ограничено это значит, что значит ограничено сверху как комплекс. Или это что-то другое значит?
Ну, как комплекс, да, я имею в виду. Правда, что-то. Это может быть и неправда. Нет, наверное, это правда. Но...
Well, so if we have a finite dimensional X, which is simply connected, then there's no guarantee we will have only a finite number of generators in M. We will have finitely many generators in each degree, yes. But then it could happen that the Postnikov tower goes on forever, even over the rationals.
Плохо-то продумал.
And there are spaces which are called hyperbolic, and one of the it's not the definition, but one of the things that happens is that for hyperbolic spaces, the number of generators grows exponentially with the degree, which is well, I don't think changes any of the arguments. It's just something that's useful to keep in mind.
Okay, so it seems like my attempt to explain it is completely wrong. So let me just formulate it with the right proposition and okay, say that. That group of automorphisms of minimal oil. I can't. Oh my God, I can't. Sorry.
Is it on my side or on your side?
I think no. I got up. It's so embarrassing. I didn't know about the limitation here. I just can't write more. Let me just open up another desk.
Please save the notes.
What?
Please save the notes.
Da, of course, I will do it. Okay, so since here, let's. Oh. Yes.
То есть это была какая-то онлайн-доска, которая работает, но в самый интересный момент выключается, правильно?
Ну, я не ожидал, извините, так.
Ничего страшного, ничего страшного. Значит, Григорий, сохраните записки. Значит, не хочется, чтобы эти записки потерялись.
Ну, я, в принципе, затехал то, что читал, потому что я знаю, читать могу тоже. Так. Если я то есть не могу, да. Ладно, давайте тогда открою какой-нибудь онлайн-доступ. Sorry for that. Так. И теперь поделиться. 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 Yes, let me formulate it. Это тоже нормально работает. So, proposition which where I stopped that automorphisms of minimal model possesses a structure of a linear dual algebraic group well, say we have case when this happens, if X is finite, say it like this, which X satisfies some finiteness condition, yes? So if X is a finite cell complex, CW complex, wait. And the second one, where there exists some number n such that fundamental group of X equals to 0 for I greater than n. Yes, so it's either bounded above by the cells or by the homotopy groups. So then, yes. Okay. So now, we didn't really understand, but we know that automorphisms are algebraic group, whether X just satisfies this condition. But recall that we actually had formula like this, yes? We had automorphisms of M factored out by some subgroup, yeah, which is precisely the maps homotopical to identity. And now we would like to wait. And well, it's not obvious whether we just factored some linear algebraic group by some subgroup. What's going to happen? We actually don't know. But let me just describe this subgroup in a very brief manner. Okay. Consider, well, first note that we will take iota as some derivation of of m of degree -1. And consider such an operator. Well, let's consider di plus iota d, where d is differential in our complex, correspond to the minimal algebra. Now, proposition that exponent of d iota plus iota d is well defined. Well, I guess you can guess how exponent should look like. We define it just as a series, and a priori we don't know whether it's good, well defined or not, because maybe. But let's prove it. It's indeed the case. It is enough to prove that. It's enough to show that di plus d is applying to some number x, and n equals to 0. That there exists some number n such that for every x in our minimal algebra, the following condition holds. Then our infinite series actually turn out to be.
By the way, it's even enough to prove that the same statement with the quantifiers reverse. For every x, there exists an n, such that.
Yes. N can be dependent on x. I mean this.
Well, as it says, as it's written, there exists an n which works for all x, which is good. But if we prove that for every x there exists an n which may depend on x, then we're still good.
Okay. And here it is important that we work in a minimal algebra setting. So recall that, like in the arbitrary case, this exponent is not well defined. So, but we work not with any algebra, but with minimal one. So recall that differential of element in minimal algebra actually lies in this in the subset of decomposable elements. So when you applying di plus id to some x and say, okay, let's assume that x is indecomposable for the sake of argument. And first we apply d, so it's becoming decomposable. So there are going to be at least two elements of which you're going to multiply. And since iota is derivation, we're still going to get a decomposable element. And the same applies here, but it's going to be easier because it's differential here. And so the idea here is that if you're applying more and more, then you're just gonna, how can I say it, increase number of elements in the decomposition of the di plus id to the power of n applied to x. But
okay, how to say this properly? M has several filtrations. It has the Bosnikov filtration, the degree filtration, and it also has a third filtration, which is given by the number of terms in monomials.
yes,
You probably won the third one, and the remark is that this operator di plus id decreases the filtration. Is this correct?
That's what I meant, but I didn't. Well,
and then why is it true?
Ooh. I thought it's probably. I thought that in case when X is finite cell complex or X's have bounded homotopy group state like that, then we have finite number of intercomposable elements, and so therefore this is to see then we can't have an arbitrary.
Well,
Way
let's see. So the operator preserves well, basically D preserves any subalgebra, and I preserves so suppose I have a subalgebra of M. Does I an arbitrary one, but CDG subalgebra? Does I preserve it?
I didn't understand. Wait, I'm sorry. I just. What do you mean by I? Oh, no, I preserve.
Well, well, the idea is we are able to prove this for an arbitrary M, for an arbitrary minimal M, if we prove it for finitely generated subalgebras and and we prove that the operator preserves all of those. So let's see. Suppose I have M equal lambda V, and inside it there's an M prime equal lambda V prime. So D has degree -1. So if we have V prime living in degree 1, then for example, then I automatically preserves it by dimension reasons. In general, this doesn't work, but we can do an induction along. We can do an induction on the Postnikov tower. Здесь можно запустить индукцию по башне Постникова. Значит, оператор не сохраняет вообще произвольные подалгебры, но он сохраняет все подалгебры, которые проходят из башни Постникова. В наших предположениях они все конечно порожденные. Ну хорошо, значит, а что нам это дает? So what's the benefit? The operator preserves all the Postnikov filtration. So we may assume M is a finite stage of the Postnikov tower. Very well. Now. How does this imply that the operator is important? То есть пусть у нас вместо M какой-то конечный этаж башни Постникова. Значит, ограничим все этим, этого достаточно. Как доказать, что, значит, что вот этот вот оператор локально нильпотентен, в том смысле, что для каждого x существует n? Значит, идея была устроить фильтрацию по степеням. Но,
Ладно.
значит, D эту фильтрацию
А.
не сохраняет. Вот у меня был какой-то образующий, я применил D, и значит, из D получилось полином. То есть фильтрация увеличилась.
Ну, да, так должно. А это сохраняет, но он не уменьшает, по крайней мере.
Вот,
Должно
значит,
быть.
что же происходит?
М. I think that.
Okay, well, let's
Fine.
well, first of all, let's ask the audience. Are there any ideas on how to prove that DI plus AD is locally null perfect? Well, it looks like the answer is no. There aren't any ideas, so let's move on.
Yeah, right. Okay. So, wait. So first, sorry, now I'm clear. So the next position. Okay, so we've defined, well, we try to define, not very successful, unfortunately, right now, this kind of operators. So assuming that we know that they're defined, at least in our case, let's prove this one. Let's show this remark. I think it's not hard, that this kind of maps exponent of d iota plus iota d is homotopic to identity. Well, it's kind of, we can write just explicitly the homotopy from M to the M tensor realgebra on T and dt is just gonna be written by the following formula. Let's say touch. It's just, I'm gonna probably abuse notation, but I will write explicitly how it acts on X. And this means that h of x equals to the following. It's equals to x plus d iota plus iota d divided by 1. This is, we're going to the x, and we're tensing this by t. And so on. So we're just tensing on the power of t from the right, and yes. So this is the formula, and this gives us the desired homotopy. Now, the main theorem, which I'm definitely not gonna prove. So theorem, which is like very important for us right now, that every map homotopic to identity have is exponent of d iota plus iota d. Now, I can't, no, I won't prove it in this talk because it's kind of, it's quite honestly straightforward, but very tedious, at least to prove that I'm aware of. I can give you the link to it. I think so. Let me, no, you can find it. For example, if you're interested in this formulas, then you can find it in the, let's say, position 10. In the paper, which is called, let me say it, which one? It's going to be Automorphisms of Spaces with finite fundamental group. And let's call it a day, because it's quite long and I don't really have time proving it. but at least I can show you why it's plausible. Let's consider this semi-example. Let's consider this kind of, okay, let's call it example. Now take, okay, it's not minimal algebra, but it's just for explain why it's some kind of plausible. Consider an algebra A, which is smooth differential forms on the smooth manifold M. Then what is a derivation of degree -1?
Well, let's write either omega or E, because this way is just one.
I'm just, I confuse this. Wait, yes. Okay, I just.
Well, let's write a star instead of infinity, because omega infinities means something else.
It's a little bit more scared. Sorry, I just confused in my head one more time. Okay, so consider this example: smooth differential forms on M. Then derivation of degree -1 iota is precisely the what called concatenation, I think, iota of x. Oh my God! But let me write not x but v.
Substitution.
Substitution. Yes. Thank you. Where v is a vector field. On M. So now from differential geometry and by the so-called Cartan's formula, we know that this stuff d iota v plus iota v d is the Lie derivative along vector field v. And so taking an exponent, it is the same as, let's say it's like taking the flow along v, vector field v. And so this theorem above, like very roughly, says that all maps homotopy to identity may be thought of as just some flows along vector fields, but yeah, that's kind of.
I think it's a very good example.
Yes, it's from Sullivan's paper. Yeah, Sullivan, very awesome paper. And now let's note something. Let's note that if let's say, let's say now some definition, just very fast one. Subgroup J is called, subgroup of GL of where is called unipotent if for every element in J minus identity is nilpotent. Now, very easy remark that exponent of nilpotent element, which is going to be a finite sum, is unipotent element. Right, I guess stuck. Now this is very easy to see because exponent of wait, just say in our case, yeah, let's write an operator. We had di iota plus iota d minus ad. And if you write as a series, we get iota plus iota d divided by 1 plus d iota d squared divided by 2 factorial plus and so on. And since we didn't prove it, and assuming that the iota plus iota d is nilpotent, we see that some power of this series is going to be 0. And so that's precisely what we needed. Okay. Okay. So now, and now the theorem that we need from the world of algebraic groups, that if J is Q linear algebraic group, and H of J is subgroup, as well as Q linear. So no, it's kind of thematic, consistent. Of unipotent elements, then we know something about factor. J factored by H is Q-linear algebraic. And this is precisely what we wanted. So now, from this, we have corollary that the automorphisms of the minimal model factored by maps homotopic to ID is Q-linear algebraic. Okay. So this is what we want in this paragraph, and we finished on it. And I think maybe there's time for a break, maybe like some logical end. Well, what now does our audience think? Should we make it or not? Like, so, okay, so let me then assume that we can make it then. I don't. Меня слышно, наверное, просто.
Егор, все это время тебя слышно было, да.
Да, просто
Я просто не мог включить микрофон, да.
Yes.
Я не против перерыва.
Да, давай, ну то как раз логично, 1:20 еще. Okay, so let's make like how much? 10 minutes is okay? Oh. Okay, let's make a 10-minute break then.
Yeah.
Okay.
where is everyone?
Егор предложил сделать перерыв на 10 минут, потому что логическая часть закончилась.
Так, хорошо. Ну, давайте тогда сделаем перерыв на 20 минут. Ну, я думаю, что да, самое время мы заслужили перерыв. Так.
Maybe I should repeat what I said. So we started in the proof. We're going by induction of Postnikov tower. We started base. Base is just an example, which was in the very first paragraph. And now I'm building a comparing map from the automorphisms of nth stage to the automorphisms of n-1 stage in order to somehow make an induction step. So for now on, I just noticed that these maps from xn to xn-1 can be thought as an inclusion of some complexes, and that's it. Okay.
So basically, every map of CW complex can be thought of as a
Yes.
vibration or a co-vibration.
Yes, it's true. But here is important that we're adding disks with the dimension at least n. Yes. Okay. So define then. So the map xn to this guy is going to be just, how can I say it? A natural inclusion is the first. Is a natural inclusion. And now we just need to define some map from coproduct to this guy. Now, in order to define map from coproduct, we just need to define a map from every term in this coproduct. So let us define map from disk to this. So we should define it in that manner that it should coincide with xn to in the boundary. So let's say this boundary. And we have some map to xn. Let's call it J. So we just need to somehow construct a lift. Oh yeah, and then we can compose it with the natural inclusion as well. So we have some map from sphere to this guy. And we just need to somehow lift this map to the whole disk. Now, this can be done if and only if this map from sphere to this guy is null homotopic. But map from this sphere to this, but remember that this guy is x minus 1, and I messed up with the indices. What in the beginning? Look, we need to kill Pn, so we need to. Oh no, we need to actually put in. Yeah, so this is n-dimensional spheroids. So we need to actually add the disks on the dimension higher up at 1. So k should be greater or equal than n plus 1. So I messed up with indices a little bit, but we're on the right track right now. Okay, right here. Plus 1, n plus 1, n plus 1. Okay, so this guy is n minus 1 stage of Postnikov tower. And well, this map lies in the homotopy group. Look at this guy. But it equals to 0. Since k minus 1 at least n, and Pn of xn minus 1 is equals to 0. So we actually have some map from disk, some lift. which coincide with the map. No. And this gives some desired automorphism of X one, this one, which we called F n from F. Now, in the similar manner, due to the fact that a lot of homotopy groups of n-1 stage of Postnikov tower are 0, we can prove that this is well defined. So if you somehow manage to find another lift, then they're going to be homotopic. It's going in a similar manner since some homotopy group of x-1 is 0. And it's obvious by construction that we have the commutative square from the formulation of this proposition. Let me just finish it. And is there any questions about it? Okay, great. So we've built some map. Note some properties. Let's say property of this map. Fn is surjective. Well, it's actually quite easy to see from our proof. Let us see it. Let J be some automorphism of x n minus 1, x n minus 1. Now, we may think again of xn as a subcomplex of xn minus 1. And note that xn, since we're getting xn minus 1 from xn by gluing disks of dimension at least n plus 1, so we have that xn is n-dimensional skeleton of this guy. And therefore, we can just define, so we can just define F as automorphism xn as restriction of J on subcomplex of xn. And this is gonna have target xn due to the cellular approximation theorem. Okay. Okay. So we have surjective map from automorphisms and stage to the automorphisms of n-1 stage. And this is surjective, so this is exact. Now, we'd like to understand, and this is kind of the hard part, the question here. What is a kernel of Fn? Now,
the kernel.
huh?
The kernel.
Yes, we can, and that's what I want to explain. Okay, so let's.
Я хотел сказать, что здесь определенный артикль.
Блин.
A kernel это
Да.
одно из многочисленных ядер.
Ну ладно, справедливо. Так, нет, извините. Так. So in order to understand that, we need to somehow deep dive in the abstraction theory from point of view of different towers, and I think get quite useful to say about this approach because I wasn't familiar with it, and maybe some people here are not as well, and maybe it's going to be useful for somebody. Okay, so let's I don't know. So we have the interlude on abstraction theory, and this is what I'm going to get us the kernel. Now, assume that we have a lifting problem, say, no, first, just so the idea here is simple. Let's say if you have lifting problem, say A to W, and we have map from A to X, and we would like somehow to continue this map. If, well, one approach is using cells on W and constructing construction theory from that. And one approach is use the right part of this diagram and work with the Postnikov tau of X. So, okay, let's write this X0. Let's say it's X is connected, so X0 is infinite. So the idea here is to try to construct a successive lifts to xi. So we build lift here, etc. And then using the fact that the inverse limit of xi is the same as x, we homotopy equivalent. So we can, if we obtain lifts for all xi's in the coherent manner, then we can actually obtain a lift for x, and we won. So we just need to understand whether or not we can lift maps in the Postnikov tau in the next stages. Okay.
Well, we did obstruction theory in the very beginning, so I don't think we need to prove everything about obstruction theory. Just please state which
I can.
Which results you use and
I want to do it this way. Yes.
And this is what you're planning to do anyway. Very well.
Okay. So the construction to the obstruction class. So okay, say if we have a lift from say W to x n-1, then we can define an obstruction class. Okay. Say omega n, which lies in the, I need to look in my notes. Which lies in the in Hn+1 of in relative homology with coefficients of the nth homotopy group of X. The theorem here is, which no, I'm not going to use, but still useful. If n equals to 0, then we can construct a lift. Oh, okay. Great. So now we need to do a little bit more about that. We need to, in order to understand the kernel, we need to introduce somewhat relative version.
Sorry. Wn is obstruction to lifting the map to which stage of the tower?
To xn.
Xn. Very well.
Okay, so in order to understand the kernel, we need to introduce some kind of relative version of Postnikov tower, so-called Moore Postnikov tower, and let me give definition of it. Okay, so if we have a map x to y F, then we can associate the following commutative diagram with it. Say X, some Z1 to Y, Z2, Z3, and so on. Here we have maps. So this kind of, such that the following holds. Let's call this map, I don't know, F. This is bad right now. Let's call it J1, H1, J2, H2, etc. So the following condition. So composition of Ji with Hi is homotopic to F. So this tower is kind of the composition of our initial map. And the following two properties. Now, map X to Zn induces ISO for, let me say it, for homotopic groups up to N, and a surjection, and the insurjection for I equals to N. Okay. Okay. And we need to say something about maps from Zn to Y. This is somewhat dual to this. They induce isomorphism for Pi for I greater than N, and an injection. For I equals to N. And, well, another one, the map in this tower from Zn plus 1 to Zn is a fibration with quite understandable fiber as well as in Poisson tower. With fiber, and let me write which fiber it is. It's, I don't need to, it's Edinburgh-MacLean space of Pn of F, and where F is a homotopy fiber of of map of X to Y. So we can apply the same idea as well as in the lifting problem to the to extension problem, yeah, to the lifting problem. Like if we have some, say, some map, some X to Y here, it's F, we have power here, this tower, and we have complex. So we can use the same idea to try to understand how lifts to the ZIs looks like and which abstraction they have. And the abstraction class to lift to need to Zn is some homological class omega n, which lies in homology. Oh, okay, it's gonna be kind of the same. It's gonna be homology omega n day, but here it's gonna be homotopy group not of X, but of homotopy phi. And so as well, the same theorem applies. If this abstraction class is 0, then we can make a desired lift. So now, how does it connect with our problem? What is the kernel of Fn is? It is some map such that So we can apply, if we take, say, if we take say, what I want to say that we can, using this Lifton problem, we can reduce it to the problem of whether two maps are homotopic or not by taking, say, we have some space and we have some, for example, homotopy. Okay, let me, as it's bad notation. Let me just rewrite it. Sorry for that. So if we consider the following Lifton problem, let's just write it. 0, 1. It's inclusion. This is map to y. It's map to x. Then we can interpret it as we have two maps which are homotopic in y, and we can try to describe whether they are homotopic in x or not. If we'll be able to construct this lift, yes. If this lift exists, that they're homotopic. So this applies to our problem. Like, why? Well, not hard to see, because the kernel of Fn is maps which are homotopic to ID in n-1th stage of Postnikov tower. Yeah. And so we can try to apply this abstraction theory. Yes, so we have the following problem. We have map from xn to xn-1. We have here, say, x 0, 1. Here's the map. Here's x, the boundary of our cylinder. And we would like to understand which map. Oh, how can I say it? Sorry, I'm just a little bit confused right now. Okay, I'm sorry for this confusion. Let me just formulate what kernel is without this motivation, because I think I'm not able to say anything good right now. Sorry about that.
Сейчас, Егор, ну давайте попробуем разобраться.
Да.
Это не бином, не тона.
Ну да, понять, я хочу просто с помощью теории препятствий описать ядро, да, то есть какие бывают. Вот. И я хочу сказать, просто элемент ядра соответствует.
So we had the right diagram and basically let's just draw the diagram again and think a little bit whilst looking at the diagram.
I want to say that the kernel of Fn is in the one-to-one correspondence with the abstraction class of this Lifton problem. Note that the homotopy fiber of this map.
Okay, so where does the so let's write this down. The abstraction class lives in which homology?
Yes, so I will write the kernel of Fn is one-to-one correspondence to the abstraction classes. That's all what I wanted to say, but I don't know why I wasn't able to say it.
Where do they live?
Yes,
Егор, где живут наши препятствия? Давайте напишем.
Let's understand. It's not so hard. So omega m lies where? It lies in the homology of n plus 1 of x times 0, 1, x times 1, with the coefficients in the Pn of f. Now, first we need to understand, okay, let's rewrite it as follows. It's H.
Okay. So the space is basically the suspension of x
Yes.
wedge S1.
So it's the same as the nth homology reduced one of x.
Сейчас, куда еще лишний фактор ушел? Значит, если мы берем, значит, x, то есть цилиндр по модулю основания, у нас получится надстройка, но еще с дополнительным фактором S1.
Ну, об этой хомотопе.
Ну, смотрите, вот если мы возьмем цилиндр, let's take x equal the circle, S1.
Да.
Let's take the quotient. The quotient will be S2 with 2 points identified.
No,
And this is S2, wedge S1.
But there's still like homotopic to the not reduced suspension.
Значит, если мы в качестве x возьмем окружность, значит, в качестве фактора значит, цилиндра по верхнему и нижнему основанию у нас получится сфера с двумя отождествленными точками, или что то же самое S2 букет S1.
Честно, почему? Я думал, что фактор, ну как?
Давайте...
мы, почему мы должны в одну точку сейчас?
Значит, ну, мы хотим, смотрите, мы хотим посчитать относительной гомологии.
Ну да, но это гомология фактора.
Значит, это приведенная гомология фактора. Значит, ну вот, значит, я утверждаю, что фактор это будет не настройка, а настройка, значит, wedge, значит, еще одна койка S1. Давайте посмотрим на примере. Давайте возьмем цилиндр, значит, самый обычный. Значит, S1 крест отрезок. Вот. И давайте схлопнем верхнее и нижнее основание в точку. Значит, получится...
ну точка одна, да, правда.
Значит, получится сфера с двумя отождествленными точками.
Не, ну подождите, ладно, наверное, надо понять, что такое фактор аккуратно тогда.
Ну,
потому что мы отождествляем, ну да, вы правы, они в одну точку схлопнутся, да, и что-то.
Значит, они схлопнутся в одну точку, и значит, значит, результат будет значит, S2 то есть S2 букет с окружностью.
Ага, да.
Вот таким образом появится лишняя паразитическая окружность.
Да, то есть будет, ну так, ну да, so yeah, it's not real suspension, it's gonna be suspension with.
Но эта окружность, она нам не очень мешает, потому что на старшей размерности она никак не влияет.
Да. Oh, yeah. Well, thank you for the clarification. Okay, and we just need to understand what Pn of F is. Homotopy fiber of map of positive tower is actually quite easy to describe. It's going to be K of Pn of X, no Xn to N. So this group is equal to homology X to the N of Xn, which is cyclic homology of X with coefficients of Pn of X. So this is where an abstraction classes live. And since the kernel, as I said, is one-to-one to abstraction classes, then this would imply that this theorem that the kernel N is the same as isomorphic to the nth homology of x with coefficients of Pn of x.
Сейчас,
Вот.
почему ядро объективно к препятствиям?
Ой, ну тут плохо, что я написал. Ну да, надо доказать. Что...
Ну, по крайней мере, давайте посмотрим еще раз на диаграмму, и, может быть, если внимательно посмотреть, то
Идея в
все
том, что
станет
там
понятно.
просто... Идея в том, что там просто... Ой, ну тут плохая, ну вот давайте. Идея в том, что там башня Постникова, вот Муру Постникова, the idea that is Muru Postnikov tower is quite simple. It has only one non-trivial k invariant. So, no, this is the only abstraction class here, because the homotopy fiber is very easy. And therefore we can, like, yes, we can prove that any abstraction class corresponds to some map. And that if abstraction class, if two maps gives the same abstraction class, then it's going to... Okay, let me just write it more positive tower for that. I think it's going to be more convenient here. Just want... Так, давайте я это куда-нибудь сюда. So I'm saying that it's going to be very simple. It's going to be x n minus 1. It's the first step. X n minus 1 on the second step. So x n minus 1 on the nth step. And here we have xn and so on. And maps here is понятно какие. The maps here are natural ones. So we have only one so the map. So if we have say diagram like this, then we actually have a map from X to the let me recall that since fundamental group of our initial spaces are simply trivial, then we can assume that these elements in Moore-Postnikov tower are forming principal fibrations. And therefore, we can think of Xn here as some of homotopy fiber of some map from Xn minus 1 to K of P and of F. And I think yes. If I didn't mess up in the indices. And so if we have, say, if we have a diagram like this, then we have a map. No, wait. Yes, so we have, сейчас, wait, so I wrote it, but oh, you wrote it. Dang. Well, how can one construct like homology class? No, yeah, we just take, if we have a map, then we take just an abstraction class, which is the only one here, because this is the only abstraction here. If we lift up to the xn, then we won. And after that, we need to prove that for any abstraction class, we have a corresponding map. And this can be done more or less by hand. I can try to do it if you... It was... Okay, so there was some mess over here, but the idea here is that it's very easy to to describe ellipse in this diagram because it has only one abstraction class, and this abstraction class precisely gives us the kernel. Now we need to prove. Let me just that. We'll say it's just one directions. If no, every omega from Hn of x with coefficients of Pn of x corresponds to some diagram like this. Let me write it again. Our lifting problem is here. So we're given some class omega of homology. Now, this class is the same. Omega can give us some map from where? From X to the K of phi n of F n. Oi, it should be. Now, oh, so can I say it precisely? Oh. Сейчас я скажу. So we have. So first note that we can. Okay, let's call this space K for the convenience. And first notice that we have a map x.01 to the x n minus 1. And here it's a K invariant. Let's fill K small of, it's on the nth stage, so it's n to the K. So there exists an say map F such that this composition is the same as, okay, let's denote this map as omega as well. No, x times 01 is multiplied to x, so it doesn't matter here. How can I thought that it was kind of simple to show, but wait. I need to think. Сейчас. Just give me just 2 minutes, I think. I did right, but I don't. Сейчас. So I remember that. Sorry for this kind of inconveniences. So we just need to raise this. Sorry about that. Okay. So, I propose that there is, so since we know that since x n to the x n minus 1 is a principle, or is principle, what do we know? We know that this is a pullback of the path loop vibration. it's xn to xn minus 1. Here is k, and here's paths on k. Wait, sorry. So we have map here that we already have, like our initial lift, and we have here. Okay. And I'm saying that we have so I'm saying that we have a map here such that the following commutes. Well, since this is a pullback, xn can be thought as let's call this map, I don't know, some letter, let's say jn, yes. So we can think of, so fiber of jn over some point is, and call this map, we'll call it, yes, okay. Is what it's, oh, I'm sorry, I'm just, is, how can I say it? Paths from image of x under this map to the base point of k. Okay. So since we know that this composition, this one is homotopic to identity, it's homotopic to identity on every component of this coproduct. Oh no, it's sorry, it's a null homotopic on each component. Then we can use this null homotopy to obtain, I will write it, since this map, let's call it J big J is null homotopic on each component. Then there exists such a map which called, H, let's say, what? But we should write it, I think there should be our map which we, wait, I'm sorry. Wait, what next? I'm just so I just get messed up something again. Wait. Yes. Okay, let's start it over again. Maybe it will be better. Maybe I will understand. Like, I'm sorry for that. I just we have.
Well, let's remind the audience what exactly we're trying to prove.
Yes, we're trying to. Let's try it again. I'm just sorry for that. The theorem that the kernel of comparative map between the stages of Postnikov tower is isomorphic to the nth homology group of X with coefficients of Pn of X. And moreover, this isomorphism is induced by taking the only abstraction class, because it's going to be only one non-zero class there, of the following Lifting problem. And the problem is as follows. We have a map from xn to xn minus 1. We have cylinder here, which maps here, which gives us a homotopy from our map to identity on xn minus 1. And here we have boundary of cylinder, and it maps somehow to xn. So this is the theory. Yes, we would like to prove it. Now, does everyone understand the statement, at least? Okay. Okay. So let's just prove it. So I propose that the proof here, it should be easy because the homotopy fiber of this map of xn to x minus 1 is quite simple. That means that we have the following Moore-Postnikov tower here. Let's say it's like this, which is very simple. It's going to be xn minus 1 is the first step. So. And on the nth step, or I think n minus 1, we have xn minus 1. Here's ID map. And after that, we have xn, and so on. And maps here are the obvious one. And here, let's me rewrite the problem. So what we can see, like in a very easy manner, we can see, at least, let's call this map, let's say, is induced, and let's call it, let's call this map omega, okay? I mean, is induced by, let's say, by map omega, which is taking the only abstraction class for the following of lifting problem. So easy part, actually, is the injectivity of omega. Yes, and where do we get this map? Yes, this map, I didn't write what. It's idea modular coproduct with F, where F is in the kernel of R Fn. And this map is a homotopy between F and ID. So let's say injectivity of omega is actually quite an easy part, which I at least can understand, because let's say let's say if omega equals to 0, then no, let me say it follows from the fact. It follows from the simple fact. That omega is the only obstruction class. So if it's 0, then we can actually lift our map and we're done. So if omega is 0, then we have homotopy between f and id on the x time on here. Yeah, so we have lift here. We have homotopy, so f is true. Yeah. So the kernel of this map is 0. This is the only obstruction class. So is it understandable, or I should try it more? Все умерли. Ужас. Okay, so inductivity of omega is quite an easy part. Now we need to somehow prove the surjectivity of this map. Now we need to prove that for every abstraction class there is a map F here, such that this lifting problem is F homotopic to identity on x in -1, such that the following lifting problem gives us this abstraction class. Well, how can we prove it? Let me think about it. It shouldn't be very hard here. Let's say we have. So first step is, it's definitely a first step here, is since omega lies in homology of x, coefficients of fiber, Pn of f is going to be equals to Pn of x. So this corresponds to some map from x to the k by n f n, which will denote an omega as well. Let's write it. And now from that we need to, what we need to do, we need to somehow wait, let me think. Oh, sure. I'm sorry for the what we need to do. I propose that we need to construct an F here, such that this all commutes, and such that the composition x equals times 1 to x and to to x n minus 1 to here k by n f n, which is k invariant here in this tower, is the same as this map. Or not? Wait, I need to just I need to. So let me just think about more. So give me just minutes. If I will understand them, we're good. If we're not, then I will just move on, I guess. Sorry for the inconvenience.
Так, что происходит? Давайте посмотрим. Значит, удалось ли нам доказать инъективность?
Ну да, это единственный такой класс, ну, единственное препятствие, которое может быть. Поэтому...
Так, хотим доказать селективность, но никак не получается.
Да, но...
Значит, ну, идея селективности в том, что отображение в KPN это то же самое, что по гомологии.
Да.
Рассмотрим, рассмотрим какой-нибудь класс как гомологии, ему соответствует отображение в KPN. Значит, KPN у нас слой, значит, из xn в xn-1.
Мне кажется, это не так. Мне кажется, я понял. Вот смотрите, у нас на самом деле там сейчас лучше это воспринимать как отображение из сейчас. У нас же там на самом деле класс лежит в относительных гомологиях каких-то, правильно? Ну, изначально. Вот только мы это факторизовали и все такое сделали. То есть на самом деле это можно воспринимать как отображение там из... Ну, там у нас стояло x... Блин, так плохо написал. Извиняюсь, что я прописываю. Можно смотреть как отображение, вот у нас x плюс 0,1, который бьет в этот k, который у нас Лимберг-Маклейн. Такое что? Там, ну, у нас получается, что k крест... Ой, x крест, простите. Ну, что x крест 0, 1, maps to... Ну, как сказать, что restriction, вот омега здесь. Сейчас, давайте я напишу по-нормальному. Such that restriction of omega on x and x times 1 is null homotopic. Так. Okay. Now I think the step 2 here, as far as I can recall, because I didn't write it down. Так, we can consider, we want to construct something like that at the end. We're going to have this xn, xn minus 1. Wait, sorry. And we need to use here, I think, that this is a pullback of path loop vibration. So, okay, we need to define, we want to define these two maps. So we already have a map here, it's given. Okay, we don't have this. Okay, let me just write it dashed. We want to build it somehow. So what we have map here, yes?
Yes, we have this arrow, and there's just one just one abstraction to letting it to x, basically to x.
Okay, and I think we have. Okay, let's just try to take. Let's call these maps which we want to build. Say, G1 and G2, for example, and let's say that. Okay, what if we take G2 as the composition x times the interval? It's maps to. It's just projection, say on the first coordinate, and we have map from the definition of Postnikov tower. Yeah. So, так, is it like say like this? Is it good map? I think what I want from this map. No, I want just to take the just trying to. So okay, if we construct if we construct some map from okay, G2 is the hard one. I don't really can recall. If so, we need to construct. Okay, let me question this. But if we G2, then we actually can have a map. Then we have one. Why? I can explain that. Okay, I want to put this diagram in the screen. So as well, xn is a pullback of path vibration. Yes. So this means that the fiber of how can I say it? So we have okay, so let me fiber of this one is well, what is it? Fiber over say some x small is let's call this map. I don't know how to call it. Let's call it
Fiber is k by n.
N. Okay.
Yes.
Kn. Let's call it Kn. Okay. Is fiber is path. No, all of the path. No.
Число отображения с xn минус 1 это kpn.
If you use the definition of path of vibration, like in natural maps, like the pre-image of over a point of this map is the path from this point to the base point.
Число отображения из pk в k это омега k.
Да, это, да.
Значит,
this space is...
значит, нужно написать правильно, куда бьет kn.
Сейчас.
Значит, kn бьет не в kpn, а в kpn, но значит, в kpn плюс 1. kpn, запятая n плюс 1.
Yeah, you're right. I even wrote it, but yeah, of x, but we should use this like this. Okay. Yeah, so we should. So we know that this composition is how can I say is null homotopic from this to what's here. It's just, and I'm saying that this null homotopy define G1 for us. Yeah, since no, let me write it. Так. Null homotopy of map x point 0 and 1 to I will not as k as well as in the previous case. K define G1. Yes. Well, it's kind of clear because how does this map look like? Well, if you take a point, say here, some point, say x small times 1. We will look up where it goes under this composition. It goes to some, say, y. And so we'll define this map in the fiber of this vibration over y as as follows. Let me write it just explicitly. Yes. So G1, let's say x1 is simply, this is the path that is defined by null homotopy of T of Kn of y. I hope it's understandable, but yes. Да. So
Почему слева
Так.
X, а справа Y? Так
так,
задумано?
нет, я просто уже не прописывал, поэтому тут что-то. Не, ну вроде это правда, да, то есть что вот у нас 0 гомотопий действительно определить такое отображение, если у нас уже 2 есть. Вот. То, что, ну что, нам нужно как бы the xn is just a pair of point xn minus 1 and just some path in k. And this path in k is defined by null homotopy of the map of from this left corner, left upper corner to this corner. Is it plausible or not?
I'm a bit lost on the indices.
Huh?
I'm a bit lost in the indices.
Yes, I just let me write it again.
Значит, Егор, я предлагаю уже прекратить мучение и пойти дальше.
Ну, учебника там этого нет. Ну ладно, хорошо. I'm very sorry for that. I'm just. Oh. Ладно, sorry. Again, I just. Okay. You're right.
Ну, в общем, идея примерно понятна, но насчет с индексом я уже тоже запутался.
Я понимаю. Ну, надо было, блин, тут доказывал, надо было записать дураке. Ну ладно, меняемся. So yeah, anyway, I just failed miserably in trying to prove this theorem. But at least, after all, I just want for you to one more time look at this, that the kernel is this homology and this morphism is induced by taking the only abstraction class. Like we were able to show the injectivity of this map, which is the easy part, only abstraction. But unfortunately, the subjectivity is, well, I wasn't able to prove it, unfortunately. Yes. Okay. But yeah, the brief idea here is that homology is the same as the map from. Now, okay, forget about that. We should then, so what in the end we obtained? We obtained an exact sequence like that. It's going to be 1 to k of Pn. Oh my God. I'm just writing up nonsense. This is the kernel of our map. It's going to be in the automorphisms of the nth stage of post-interrupt. The automorphisms. This one to the one. Так. Okay. Now, we can apply the same theorem. Well, let's say we have Postnikov tower for X. Some kind of. And we can construct a Postnikov tower for, oh my God, and this is not here. This should be superstrings. Okay. And we can, okay, this is normal X, and this is localization of X. And this can be X 0, 1, X 0, 2. Okay, and here's maps. Here's the maps. Well, one can apply the same theorem for the Postnikov tower for rationalization of X and obtain the following exact sequence as well. Oi, not here, over here. It's gonna be X. Well, since rational homology of X and rational localization of X are equal, we can write like this. En of X tensor over Q. Here we have automorphism. And morphism of X n minus 1 of 1. Okay. So this is just obtained from localization. Yeah. Moreover, one can see that we have a natural map. Let me write it again. We have here 1 homology of X, say X. Automorphism of X n automorphism. Oh, sorry. Automorphism of X n minus 1. 1, and we're gonna have this. Morphisms of X. And we have maps here, which is induced by localization of the corresponding stages of Postnikov tower. And here we have just simple tensoring over Q. Well, okay, so-called R1, R2, and R3. So by induction, so now we can apply an induction hypothesis. By induction hypothesis, R3 realize automorphisms of X n minus 1 as an arithmetic subgroup of the corresponding automorphisms of localization. Oh, okay. And actually, we can see that just no, we can see the same oh, note that why doesn't I'm sorry, what happened? I just can't move. Okay. Сейчас произошло с пером, я подождите. So just so. Тирон не может писать. Сейчас странно. Почему я не могу писать? Ужас какой-то. Нужно надо обновить. Okay, I think I could. Sorry for that. Okay, note. Okay, let me just I need to do it so we can see. Okay. Note that the map R1 is realizing the corresponding homology as arithmetic subgroup of rational homology. Yes. This is just some. Yes, this follows from the fact that Pn is finitely generated group for a simple connected space, since we live in finite dimensional, since X is finite dimensional. Therefore, the homology is finitely generated, and we can apply more or less the same. You can say. We can do almost the same as we did in the example at the beginning of this talk. Yes. So we can factor by all torsion elements. It's just finite kernel, and then we have an inclusion as some homotopies, which are maps which are homotopical to identity, but as an integer, as an arithmetic subgroup, something like that. Okay. So yeah. So this is why R1 is realizing as well. We can factor out about all torsion elements, this is finite kernel. And then we have an inclusion as an arithmetic subgroup in the vector space of homology tensor Q. Therefore, we can use we can deduce from that and from the fact from the second paragraph. I'm sorry for that. I'm just deduce that R2 is realizing as well. And so we proved what? We proved that automorphisms of X of nth stage of Postnikov tower is what? Is this is arithmetic. Arithmetic. Now, if we have now we would like to somehow pass a limit, but it's not really possible. But there's a theorem that ends it all, and this is the final one, and it's gonna be easy. The theorem which is gonna be end if X, which is kind of was counterintuitive for me, but if X as n dimensional finite complex, then what we have that automorphisms of X are indeed isomorphic to the automorphisms of nth stage of Postnikov tower. Okay, I think it's a theorem. Well, if we prove it, then we are done, because we prove that automorphism of any stage or any finite stage is arithmetic. So we will be done here. Now it's gonna take, I hope, less 5 minutes. And this is something that was so hard to prove. Well, we can apply the same abstraction theory, but it's gonna be easier this time. First, note that we built, if you can remember, we built some maps from automorphisms of Xn to automorphisms of Xn minus 1. In the same manner, we can construct a map F from automorphisms of X to automorphisms of X to the nth stage of tau. Yeah? Сказать или просто? Just, sorry. Okay. Now, if you recall, we built this by viewing the corresponding map in the Postnikov tower as an inclusion of subcomplex, and then we kind of just extended the map. And we can do just the same over here. Nothing really changes. And we can actually, one of the property, which we've essentially already proved when we work with stages of Postnikov tower, that F is surjective. We can just apply the same thought. Argument, yes. Thank you. We can apply the same argument and we can apply that F is surjective. Now we just need to prove that the kernel of F is 0. Well, this is not very hard to prove. We already saw that abstraction classes for this problem, may I remind you, we had a problem like this. Here's gonna be like that. Gonna be an X and stage. X, okay. And we'll like to build here. So abstraction lies in what? Omega M, let's say. They lie in the cohomology, M cohomology, of X with coefficient of EM of homotopy fiber of this map. These maps. But homotopy fiber, what we know? We know that homotopy fiber of this map satisfies the following: PM of F. Since this map is an isomorphism for all first n homotopy groups, M of F equals to 0 if M strictly greater than n. Oh, no.
I think we want to use that the cohomology of X vanishes for
M
in a high degree.
And since since X is n-dimensional, the homology of M of X with any coefficient is equals to 0 for every M strictly greater than n. So we have that all abstractions are 0, and we have this map, and this map gives us that show that F is injective.
Very well.
And we're done. That's all. I'm already in a lot, so.
Well, are there any questions? Yegor, please save the notes.
Да, of course, if it's.
Okay, let's thank the speaker. The topic wasn't an easy one, and we saw the main steps of the argument. We weren't able to check all of them, but at least the general strategy was reasonably clear. Okay, so let's turn off the recording, stop recording.